thank you for being here. I'm going to be talking about machine learning operationalization. Don't expect a technical talk. It's not going to be sexy algorithms. It's going to be all the unsexy bits that are required to get your machine learning models actually solving real-world problems. So, just a quick intro. My name is Yann. I've been in data science and machine learning for about 20 years. I've been at companies like Netflix, Yahoo, so Scale. I joined Delivery Hero in Berlin a year ago, about. Delivery Hero is a company that is a global company about food delivery. And when you're operating at that scale, the question of how do you operationalize the whole process of getting your models in production, getting the right models, getting them working well, becomes really important. It's not just about getting an algorithm to succeed, it's about literally building a machines of putting data science models and solving business problems with data science. So there is a lot of hype about data science. There is a lot of, it's still relatively new. Data science was not really a word that was used mainstream before 5 years ago. So show of hands, how many in the audience say they are data scientists? Okay, few. How many say they are a machine learning engineer? Okay, some overlap there, that's good. So that hype basically is data science is the job of the century. It's one of the defining jobs of the 2010s, 2020s. And well, maybe it's a little overhype. So, you know, Harvard Business Review says data scientist is the sexiest job of the 21st century. It's consistently rated as the best job to be in. It's also the most in demand. A lot of companies are saying, we need more data scientists, we can't get enough. This is the kind of skill sets that we're missing in our environment. So everything is peachy, right? That should be the best thing, and that should be really great. But is it really the best job? Well, you know, data scientists say, that's great, we're very much in demand, but we spend a lot of time doing stuff we don't like. We spend a lot of time doing data cleaning, data sourcing, data preparation, and all those things that are not the sexy algorithm bits, not the actually cool generative adversarial network that I want to play with, right? It's just asking a bunch of people in other parts of the company about where can I get my hands on this data? And everybody hates that. And then companies that are such in demand of data scientists actually are not seeing as much success as you would expect from it. There isn't a lot of public data that I've been able to get my hands on, but from past experience and from the little bits, you can start painting a picture. When you're asking companies about where they are at in their data science and machine learning journey, a lot of them are just interested, but haven't really started. Some have dabbled a little bit, but are yet to see, you know, real concrete output from a business perspective. And there is only a very small number, less than 15%, that are really into it, that have seen concrete results where it's actually moving the business along. I have less data on the success rate inside the companies. Anecdotally, what I have seen is that you have maybe 10 to 20% of data science projects that actually make it in production and actually start building value for the company. So it's not that great, actually. There was a really good paper that I recommend from Google a couple of years back that was looking at machine learning relatively systematically, and you can expect Google to have lots of data about that at the meta level. And I was saying, well, okay, that's a great tool, but it's expensive to run. It's really complex to run at scale, not just because of the amount of data, but because of the organizational complexity of it. So that's the kind of stuff that we're going to look at. I don't have any magic answer today, but I can point you at ways of reasoning, way of seeing things that might help your journey a little bit. For all the technical people in here, I think this is helpful because that gives you a little bit the context through which you can help your manager, help your organization, do the right things and basically remove all the unsexy bits out of your journey. For the people who are thinking about data science today, it's a way to avoid some pitfalls. For all the others, it's maybe some recipes on how to think about the world landscape and what to do. So why is it complex? Well, when you think about data science, you say, all right, I have my data. I'm going to deploy some algorithms, some machine learning code. And hey, magic, I'm going to have some value out of this. I'm going to have better personalization, make my customers happier, optimize my fleet, optimize my business. It's going to be great, right? Yeah, but actually, this little green box in the middle is a small box out of a landscape if you want to actually deploy that in production. You need to get data in, validate your data to make sure that it's not garbage, do data engineering to transform it, extract your features, match historical data that, well, model might have changed and things like that. That's engineering. Once you have your algorithms, you can actually do predictions, you can actually do generation, you actually have to serve the results, so you need to have a really basic serving infrastructure, actually get that into your product as a feature. You need to understand whether it's any good, so you need to have analytics, monitoring, metrics on top of that to measure the performance of your model on a continued basis, to do A/B testing, to do whatnot. It's barely any different, in fact, from, I would say, a non-smart, non-machine learning-based feature in a software product, but that's a problem that still exists. And it's made more complicated because in machine learning, you're handling lots of data. So you have all the infrastructure, all the logistics of getting the data in, monitoring quality, getting the data out, monitoring your models, doing model versioning and all of that. That gets complex. That's a lot of engineering that you're going to spend on really the logistics of your machine learning models, not the science, not the algorithms. And then, okay, you have a software product that you're trying to deploy at scale. There is DevOps in that picture, right? Configuration management. Performance and cost, because you don't want your Amazon or Google cost to run out of control. You're monitoring to make sure that your infrastructure is stable and scales well. Change management, security, and all those aspects that you have to deal with. By the way, the size of those boxes, I have actually taken from a paper I don't remember the name of, so that will come back. It's about representative of the amount of engineering effort, good proxy lines of code that get into real-world machine learning-based feature like personalization or fleet optimization or time prediction or things like that. Anecdotally at Delivery.io, this is also pretty representative of the amount of code that we spend on those different bits of our machine learning infrastructure. So you'd say, all right, I'm done with all the unsexy bits. That's it. Well, actually not quite. It's even worse than that. If you look at this middle picture, this is the real engineering. And then there is all the parts of running a successful business around it. You're building customer-facing features or business-facing features if you are in a B2B context. But you still need to care about customer experience. So you need product management. You need customer journey management, design, and all of those things. And you actually need to tailor those to machine learning. Very simple anecdote on this. If you're asking questions of your customers in a machine learning context, you need to tailor them to get the right answers. If you want good quality data, that means a slightly different product design approach. You're going to have to integrate that. So yeah, the fact that you're doing machine learning here is actually relevant to the size of this box and the level of education of your designers and front-end engineers, etc. You need product. You need to understand what your customer needs and how to serve it. If you're doing personalization, for instance, that becomes a complex topic. You need to manage quality and support and all of that. And then, well, you need to run a business. So you need to have operations. At Delivery.io, we are running in 34 countries. So that means we have to have boots on the ground in all those countries. So there is some aspects of that. Market understanding, because you don't want to stand still, otherwise competition is going to eat your lunch. And, well, to do all of that, you're going to have a bunch of people. So you need talent management and developing your people, training, hiring, etc. And since you have a lot of data, you also need to address compliance. Not just GDPR, but all the exposure that comes from data breaches and the proper use of data, etc. This is actually significant. You can need to have a pretty significant legal team if you're doing machine learning. So remember where we started about the machine learning algorithm? This is the very small green box in the middle, and that actually represents the amount of effort that you have to put in it to really do machine learning at scale. Proxy, number of lines of code, proxy, number of people, but essentially that's a lot of investment that doesn't go into the sexy bits. So you say, okay, but is it still worth doing machine learning given how complex it is? Well, first, yes, it's complex, but so is any other software or web product. You are going to have to do this. Second, there is actually ways to streamline this, to make this palatable, manageable. Remember, I said earlier I wasn't going to be technical. We're literally completely away from the technology, by the way, at this point. So when you're looking at that whole process, right, it's a loop, and it's really an iterative loop. I'm not going to go over the graphic in the middle, but really, if you're looking on the right, there is something a little bit flagrant when we're thinking about machine learning. There is a giant amount of focus in talks and conferences like this on the machine learning bits, the algorithms. But when you're looking at where companies spend their effort, it's everything else. That's not necessarily great to paint a realistic picture of machine learning or to make it actionable in most businesses. And all those bits of feature engineering, reliability engineering, etc., change management, this is all engineering here. I haven't even painted the picture of the business in the main wheel. So how do we get to optimize this stuff? And I assure you, there is a way. It's not going to be magical. It's a lot of hard work, but there is a way to make it less painful. So sorry about this slide. It's a little messed up because of different format, but essentially, that whole effort, like that horizontal bit here, that is the real effort that you realize you're having. There is ways to reduce it. On one hand, by automating all the things that are automatable, all the things that can actually be done by a piece of software running on a machine, a shell script, whatever. On the other hand, the human aspects, where you can lay down process work, structure, so that your human-based processes are efficient, are reproducible and well-controlled. And what remains is the middle. And the middle is probably a little bit more than what you were expecting to spend in terms of effort on a successful machine learning solution, but it's not completely out of control. So I think you have to think of, at the platform level, the automation bits. It's really about the bytes, the technology, right? Is your technical capabilities. Do I have easy ways to ingest data, to transport data for my data scientists, but also the random Joe in QA that wants to understand why this thing is not working on the specific platform, to access the data easily, to do a simple SQL query to figure out, hey, I have this weird bug on Android just because the screen format is a little bit different. Now I understand and I can actually fix that. Data discovery, at large scale, you are going to have hundreds of data sets. If they are all over different infrastructure, different formats, etc., your data scientist can say, I'm going to use those two data sets that I actually have access to and miss on a whole bunch of refinement of my models, a whole bunch of features that I could potentially use, but I don't even know I can. I don't even know I have the data because it's locked somewhere else. Data inventory, making sure that you don't have endless data duplication or slightly diverging accounts of what happened to your customers and not knowing which to trust. So refining your data and normalizing that a bit. Data monitoring. You don't want a small change in your product completely destroying the quality of your data and therefore the performance of your models downstream. And because it's going to be a complex infrastructure, you want orchestration between your data transformations and the actual capacity to transform at scale, right? You don't want all your models to be running scikit on a local machine, but actually be able to run in the cloud automated at scale and not have to worry about, oh, we all of a sudden have a spike of orders and my training is failing this week because I have too much data. Oops. So that's the technical platform that you need to progressively put in place to reduce those pain points about the basics of data engineering, the basics of model training, etc. Then there is also all the enablement around data. Having mechanisms to do data sourcing from your backend database, from external data sources, etc. Standardizing a little bit the way you do enrichment. You don't want to have to reinvent 20 different ways to transform a GPS coordinate or set of GPS coordinates into street addresses, for instance. A bit of visualization, because you don't want every single engineer that is doing things with data to have to learn high charts of all these three. Reporting, your business types are going to have to need a way to come in and understand what's the evolution of your model performance and if your data science investment is going in the right spot. And of course, I've mentioned compliance. You have lots of data, so you need to be able to do governance and compliance. On the other side, the human aspects, right? It's about organizational capabilities. Well understanding your strategy and where data comes into play in that strategy. Basically, what's the role of data into executing your company's strategy? Because you're only going to need that to know where to invest. Tracking your progress, how fast your maturity in terms of quality of your model, sophistication of your use cases, but also availability of those technical bits on the other side comes into play. Ownership, because you want to have a clear line of control about what gets into it. And other things like team collaboration. If you have large teams, that's going to be important pretty quickly, especially distributed teams like we have here. Hiring, training, and all those aspects. So sorry about the rest of that slide that is a little bit messed up, and I'm going to talk through it. But at the end of the day, you want also to very carefully inventory and manage your data assets. Data is really valuable if you know where it is, if you know what it is, if you know how good that is. It's worthless if you don't know any of those things. So you're really going to have to put numbers on those, right? Understand your business logic, where it goes, and be able to understand your calculations and derivations and have an inventory of this so you don't keep rebuilding those because you have forgotten them. Have a clear hierarchy of KPIs and stuff like that. So at the end of the day, you're going to invest into those bits, those technical bits on one hand and those organizational bits on the other hand. It's on one hand about automating things that you do every day as a data scientist. You want to do data sourcing, and finding data is what a lot of us do. Well, you're going to have mechanisms for that. Data is decays, ingestion method, etc., so that when you have either an external data set that a vendor provides you or some data that is in one of your backends, you have a good way to get it in without spending 6 months actually building brand new engineering to actually make that reliable. Data access. If, as a data scientist, I want to figure out what do I know about addresses in this country, you don't want to spend 2 months trying to figure out who knows about it in the company, who can help you, who can actually grant you access to the data, who has the credentials to the database to actually connect your ingestors to it, etc. So you want to automate this bit. You want some data governance and a place where you can find and access data. Data discovery, you want to really understand what does that data mean, how is it collected, how is it linking to other things, etc. So for that, you want to be able to do a data inventory, and typically that comes through the the process of having a data catalog that embodies physically those characteristics. That is going to list all your data sets and list all the information that you have and list all the relationships, etc. It's not a relational database because we are talking about big data, but you still need to have that information. It's about knowledge management, essentially. Data quality management. I've mentioned that a couple of times, and you will see that's a leitmotif, but really, if you have garbage data, it's worthless. You have spent all that effort, all that engineering for nothing. So you really want to monitor your data quality and make sure that you can actually track it over time. So that means having quality validation mechanisms, schema validation, but also quality measurement, etc. And you need to track it. You need to have dashboards so that when one of your backend engineers makes a subtle change in the way a hash is computed, that doesn't destroy all the value of your data and your ability to join. Or if that happens, you see it really quickly so that that change can be reverted. So you want tracking. Data preparation. a lot of us spend time doing cleanup, enrichment, feature engineering, and all that stuff. So you want good mechanisms to do that and good mechanisms to not duplicate that effort. If you have more than one data science team, what typically happens if you don't have that is that they are going to independently rebuild the same features. Well, that would be better if they could collaborate, right? And then, hey, larger teams. At Delivery Hero, we have about 150 data scientists and data engineers in Berlin alone. That means multiple teams. That means also a lot of burden of coordination. I'm running a model. I want to validate it against this data set that another team is generating. How do I communicate? How do I exchange my stuff? Jupyter notebooks, yeah, okay, that works, that's great. But if I want to collaboratively edit my Jupyter notebooks, that doesn't come out of the box. So you're going to have collaboration tools in that picture. And then, okay, you're doing engineering, you want to know how good it is. So you need to be able to evaluate your models, not just, okay, I have a model, precision, recall, what does that mean for the business? From a business perspective, those metrics are pretty useless. They are useful for the data scientists to understand what's happening, but you want to correlate that with business KPIs, customer conversion, customer retention, and things like that. If you can't do that, if you don't have a good way for your data scientist to actually measure the impact directly on your business metrics of what's happening, then you have a gap here. And then all of that needs to go in production at some point. And not need 2 weeks of 3-team coordinating for that to happen. So you need to have a seamless way to do that. That means CI/CD, that means environments and validation methods, that means an artifact promotion process, and all those things. Those are technical bits, things that typically don't even come out of the box. Also, you're going to have some tools if you are in a cloud environment, but you're going to have to build some stuff to make that happen reliably in your environment. And then, okay, that has been deployed in production, it's running, it's fine, I'm happy, I'm done. No, I'm not quite done. I need to ensure that when I have a spike of traffic because it's Easter and I suddenly have 4 times the number of orders because a lot of people are just ordering food at home, my infrastructure actually can scale. And I don't have all of a sudden, because I have a different data sets coming in live, my model performance degrading. So I need to do monitoring, I need to do orchestration, I need to be able to do rollback, I need to do canary ramp up and ramp down of my different versions of the model and things like that. All of that is what you're going to need at some point of maturity, at some point of scaling in your data platform. Just a quick peek at what that looks like at Delivery Hero. It's a very high-level model. I have not mentioned any technology here, but you can see the path, right? From producers to ingestion to transportation to access. And then the data science bit on one end, the more classical data warehouse stuff on the other end around analytics. And then data quality management, data catalog for your inventory, and the processing ability and orchestration ability that come into it. So those are the relationships between those different capabilities, different features of your data platform that you're going to need. That's for the infrastructure and software, I would say. And then that's for the data. You get data in. Not all your data is going to be nice and good and correct, so you're going to have to validate your data and set aside invalid data that you can't use. Not all your data is going to come in at the same time because your Middle East deployment had a downtime, and so when it recovers, data is going to come a couple hours late. Well, okay, you have to handle this. You need to deduplicate, enrich, clean up your data, and do a bunch of derivations for various purposes on top of that. You actually have to think about data architecture and where you're going to operate the different bits. The top is more data warehousey, more analytical. The bottom is more about the data science process, the feature engineering, etc. But ideally, you don't want those two infrastructures or those two methodologies to be very far apart. Because what your data warehouse team is doing building KPIs, you're going to need to integrate into your machine learning and data science process. Yours might differ. You might organize things differently. You might prioritize also building some parts of this differently. But at the end of the day, you're going to need some similar capabilities at some point of your journey. It's good to have thought about them when you start, or at some point of the process when you start standardizing a little bit your approach, thinking about the future to know what's on the path. So the other side of this is the human factor, all the processes, all the collaboration methods, all the organizational structure aspects of really doing data science and machine learning at scale. And it's less about really optimizing how fast you're going and more about optimizing how predictable it is. When you're building product features, it's not so important to know that it's going to come in 2 months or rather than 3 months. What's really important is that you know it's going to come within 3 months, not 6, not 1, right? That predictability is the critical bit. Same thing applies for data science and machine learning. So you have to think about your process. Your data science team is going to go through a number of steps with a number of factors, a number of coordinations. At the beginning, you need to start to understand what is it you're building. What problem are you trying to solve with machine learning, with data science? Defining your product, essentially. The customer problem, the customer use case, and how machine learning helps solve it. Here, you're going to interact with a business sponsor, typically someone who has a cool idea on how to make money. That's how it happens in such environments. And a product manager to define the product, and a data analyst. They say, is there even an opportunity here? Can I put that in shape? Can I measure it? Am I going to be successful? Is there a market for that, etc.? So you're going to need to start digging into the data. This is, I would say, more business intelligence side, but it's really about, okay, do we have an opportunity? Do we have a product to build? The driver at this stage of what's happening for this feature is going to be your product manager. And yes, you're going to need someone who has the product management hat. It can be a data scientist with a product owner kind of slant, but you're going to need someone really thinking about the customer there and what you're building. Next step, getting data in. Do I even have the right data to solve this problem, or do I need to change my product or to change my approach to get the right data in so I actually know how to solve this thing? You're going to have a product manager, but that's where typically you're going to work heavily with domain experts, the people who know your business really well. The people on the ground who know how to optimize logistics for us, the people who know the restaurant business for us. Your business is going to be different, so that's going to be a different person. But you really need to understand the dynamics of your market, whether those things that you're seeing in the data even make sense. Same thing. Your data analyst is going to be very present there. Or your data scientist that is double hatting as a data analyst for that period of time if you have a smaller team. After that, you really transition to the data engineering and data discovery side of things, right? Defining how you're going to measure that impact on your customers, that impact on your business, figuring the right KPIs to measure the impact. Still, your PM is going to be there, but you're going to start doing data engineering to really get the data in shape so that you can measure things. The data scientist, in a lot of cases, or your data engineer is going to be driving a lot of that. But this is more on the data exploration, more on the investigation side. So this is why typically I would think the data scientist is the one taking front on this and really driving those efforts. Once you have your data, you're going to do feature engineering, trying to figure out, based on what can I predict, based on what can I classify, what is it in the data that is critical for my understanding of the space. Data scientist, of course, is primary here. Domain expert, again, to understand the significance of your feature. It's not just a question of building data features and throwing things at the wall until it sticks. You need to have a little bit of domain expertise there injected. And then, of course, data engineers to make that reliable. Because, no, it's not just data wrangling on your laptop. If you're dealing the robust data pipeline building toward the end of this process, you're going to be missing in data science velocity. So you really want at this stage to start building robust features and have reliable ways to compute them and generate them on an ongoing basis. So that's where your data engineer starts being involved. Then, of course, the part we love, model training, where you really apply your algorithms, you figure out the best one, you figure out how to measure your performance and what's the best approach, and you tweak your algorithms. That's really where your data scientist and your data engineer are going to collaborate really closely to get the right data in the right place with the right models. And okay, I've said the data engineer takes the lead there. Why? Well, because when you're building your model, you need to think about how am I going to go to production, right? Do I have something that scales? Do I have something that is going to be deployable in a real live environment? Can I deploy this thing without downtime? If I really have collocated my model serving and my model training, I might have a problem. So that's a really important collaboration. And then, okay, that's where we go to production. By this point, I'm expecting that your vitals about your model performance is good and well. You have done enough analysis of the correlation between that and your business KPIs so that you understand that it's likely to be successful. You don't necessarily know, but it's likely. So you go to production, ideally canary deployments, so that you can roll back if really the reality is not matching your expectations. This point is still collaboration between data scientist and data engineer, but this is where your DevOps or infrastructure engineer or system engineer is going to come in and say, all right, how do I scale this? How do I deploy this in multiple regions, etc. And then, okay, it's in production, it's live, it's showing to your customers. You actually can measure the real-world impact of this. Ideally, through your efforts on data infrastructure and platform, you have a good way to do A/B testing, so you have a good way to test this validity of your model in the real world. You're going to optimize. Your first shot is probably not going to be that great because you don't have the right features, because you have taken the wrong option in model serving and things like that. So you're going to close that loop. You're going to iterate from model optimization to back to feature engineering a couple of times. Perhaps even to KPI definitions, because you realize that actually your leading KPIs are not so good, and the impact that you're expecting on your trailing KPIs is not materializing. So you're going to adjust that a couple of times. You're going to go through that loop a couple of times. This is why it's really important to have streamlined the steps between KPI definition and model optimization, because every slowdown, every extra hour that your data scientist needs to deploy their model or to validate that they are good is going to slow down your innovation, slow down your iterations, slow down how fast you can refine your models. You want that to be very, very streamlined and be able to iterate through this on a daily or weekly basis, not a quarterly basis. So at some point, you really, through A/B testing, really have done something that works. You release it for everybody. You really want to close that loop and say, is this really moving my business KPIs? Am I making more money? Am I getting more loyalty from my customers? The things that are really important for the conduct of your business. And close that loop through experimentation to your product definition. Okay. I had this great idea for a feature. It's powered by machine learning. It's performing well. People are using it. People are loving it. But fundamentally, my customers are not stickier. What did I go wrong? This is where you go back to the product definition and iteration and say, well, actually, maybe we didn't really understand our customer workflows. That's where product analytics and things like that are going to come into play. I haven't really represented that in there, but it's there too. So what's really important, I was mentioning the speed at which you can go through those steps. You're going to have to continuously monitor that and optimize it. There is a couple of metrics that I've mentioned here. There is literally dozens of metrics that you could throw at this process to optimize it. But there is a couple that are useful. Lead time. How quickly you can start working on a feature. It boils down to team capacity on one hand, but also how quickly you can refine your approach so that it's clear to the team and the team can start executing. Model performance, of course, we all have that. We have different metrics, but you're going to have to measure that. And then release velocity. How many releases a day you can do. That's going to be really important to really get that agility into place and iterate through this loop quickly. I'm not saying those are the best metrics or even a precise definition of what metric you're going to use and how to compute it, but those are things to think of. You need to measure the performance of this process. The other bit of that, I was alluding to that, is data capital. You're going to accumulate data, and upstream of your whole data science process, you're going to say, am I building the right data sets for the next project I have, not the one I'm building right now, but the next one? Am I going to have the right tools, the right assets, the right knowledge about my customers, my market, my environment, my business? So for that, you really need to think of data as an asset. It's something that is valuable, just as valuable as your machines, your engineer, your intellectual property, your machines if you are in manufacturing or in physical industry, etc. So you need to inventory all the data you have quality targets to make sure that it's actually usable and decent. And ideally, it's a good practice to report on that regularly at the C-level, to create attention to it, to create the capability to have dedicated investment to this, but also align everybody on, yeah, data matters, and it's worth that much for us. Then there is also all the domain knowledge and all the, I would say, software knowledge. That means inner sourcing. When you build a block of code, right? Everybody in the company should be able to have access to it and reuse it. Not have two different teams reinventing the wheel or rebuilding a feature because they can't communicate, they don't have a good way to exchange their code. And ideally, they should be able to collaborate really easily. Just use Git and use it well and have multiple projects, but make sure that things are open within the company. Have good conventions so that different teams can interoperate and communicate pretty clearly. Having naming and coding conventions and standards, and actually having advocates on the team to follow those so that your code doesn't become dead because the other team is not able to update it because the conventions are completely different and the naming is obscure, etc. You want to support that code level collaboration. And then community. Especially if you have multiple engineering locations, it's very quick to have separate cultures, to have teams that don't talk to each other, that stay in a little closed space. You want to put in place mechanisms so that teams can exchange, can still teach to each other, can still collectively come up to those conventions and standards and develop those from the ground up and keep them updated and living. So that means building community, building mechanisms so that teams get together, talk to each other, present to each other, etc. This is a really important and healthy mechanism. So that's for the, I would say, more talent level thing or more organizational level things. It's by no means an exhaustive list of things you can do, but it's a couple of things that I hope are helpful and that you can think about when you're building the next steps in your data science journey, or even starting on that path and knowing what's ahead of you and say, all right, maybe in a month, a year, 3 years, I'm going to have to think about those things, and I'm going to have to think about how am I going to invest in that? What's the sequence? What's the level of investment? When does it start becoming critical, etc.? So that's it. Thank you so much, and I'm expecting a lot of questions.
And questions on the screen, please.
Oh, that's an interesting one. Well, data validation can fail in many different ways. Sure, you have this field, and it should be a date. OK, that's great. A date of what? A date of when your customer passed the order, a date of when you received the order, a date of when the call hits your backend server. The semantics of that can be pretty important, and it's really hard to validate. It's really hard to validate that, yeah, sure, it looks like a date. Is it the right date? Is it even in the right time zone? Am I getting UTC or local time zone, right? At the end of the day, why it does influence data science project? Well, what I've just described is fundamentally different semantics of when your order was passed. If that's the date, the timestamps at which you're thinking your order is passed, if you're trying to compute, let's say, a delivery time based on that, you're going to have completely different results depending on the semantics. So if you have multiple locations, multiple backend systems, and you have one team that ascribes one semantic to this timestamp and a team that ascribes a different one, You're going to build your model. It's going to be great in one country and fail miserably in the other one because of slightly different semantics. Oops. I don't have the magic answer on how you validate that, but it's really about the semantics, and you need to pay close attention to it. I hope that answered the question. Total data people in Berlin, which is our main headquarters, is 150 people. Data engineers, data scientists, data analysts, anybody who feels that they have data in their title. Globally, about 300, 350. It's hard to guess because some of those roles are a little bit fuzzy. You know, if I am in product analytics, am I a PM or am I a product analyst? Well, sometimes a little bit of both. But yeah, roughly a couple hundred people worldwide.
This is the last one.
This is the last one? All right, come on.
The audience, do you have a question? No?
All right, well, thank you so much.